Hello, this is Mr. Schultz here with you. Going to take a look at lesson 723. So 723 says this. Students will identify slopes, and slopes are what we talked about yesterday. It's basically that steepness on the graph. So students will identify slopes from graphs and will recognize the effect of scaling the steepness of a line. So let's see what this looks like. So how can I find the slope ratio? So slope in different representations. So start off, it says in 722, you learned about how to use a number to describe the steepness of a line. Today you will work with different representations of lines and look for how the slope can be found in each representation. As you work with your study team today, keep the following questions in mind. What is being compared to find the slope ratio? What would it look like in another representation? So let's keep going. Now this next question here is big and has lots of parts, so I'll kind of read the whole thing and then we'll go on to the next page where it'll be summarized here. So, a planting manual printed the graphs below so that gardeners could predict the height of trees after planting. Jill wants to figure out the rate that each tree will grow. She remembers that the slope is the ratio of the vertical change to the horizontal change between any 2 points on a line. The units for the vertical change are the same as the y-axis, and the units for the horizontal change are the same as the x-axis. Finding the slope for each graph will allow her to compare the change in height over time. So just that change in y, or the change in the vertical versus the change in the horizontal there. So part A says this. On the 7.2.3 resource page, which is on the next page, draw and label a slope triangle on the graph of on the line in graph I. Write the slope ratio and decide how fast the tree in graph I grows. In part B it says, can you find the slope of the graph of graph 2 just by looking at the line, y or y not? And we're going to talk about these things called lattice points, and this is just where the grid lines intersect. So these are showing two lattice points here. So it looks like this line is intersecting the grid right on those points. These are easier points to use than, say, something like this, because we don't know exactly what the y value is there. You know, it's kind of partially between, is that 3/4, is that 0.6? This one too is also tough, as well as this. This is hard to use because I don't know exactly what that x point is. But a point like this is a great lattice point because it's crossing at both the y and the x axis there. So that's what part B is talking about there. And then in part C, you'll be using a similar thing, but this time doing with graphs 3 and 4. So let's just take a look at what this looks like, and I think the next page will make more sense. Okay, so here's 743, and it is summarized. Here are the graphs that they're talking about, 1, 2, 3, and 4. So the first one says, draw and label slope, and this is referring to just graph I here, and then write the slope ratio. So take a second, see if you can pull back what you did yesterday, and draw the slope triangle, and see if you can write that slope ratio. And I'll come back in just a second here. Okay, so lots of different ways to draw this. The way that jumps out to me would just be something like this. But you could have drawn this all kinds of different ways. You might have drawn something like this. You might have drawn something like this. All kinds of different options there. But let's just go with this red line here first, because that's just the way that I saw it. So it says draw and label the slopes. So I need to now label this. This is going up 2, and it's going over 1. It says write the slope ratio. So remember that we do the... Now this ratio has been talked about a little bit, but as far as which number goes first, because some people might write this as 1 over 2, and some people might write it as 2 over 1. Well, which of them is it? So remember that we're looking to do this as kind of a unit rate. And so time in years here is what's going to go in the bottom. You can also think about this as being rise over run. So here I am rising or going up 2 meters for every 1 year. So I'm going 2 over 1 as my slope ratio. So let me just write that right down here. That would be 2 over 1. You can think about that as rise over run. So what am I going up in the y-axis versus what am I moving to the right and to the left? How fast does the tree grow? Well, 2 over 1, we can simplify that to be 2. So what that means is that that's growing 2 meters every 1 year. So it's growing 2 meters per year because it's growing up 2 meters for every 1 year that it moves over. There's that 2 over 1 again. Let's take a look at part B. What is the slope of graph 2? And don't forget to use your lattice points and write the slope ratio. So again, reminder that the lattice points, those are those easy crossing points. So here, this has got more points that are a little bit harder to see. Like right about here, I don't exactly know what that X value is. I don't exactly know what that Y value is. So look for those kind of natural crossing points where both of the grid lines match up. So it looks like I've got one right here. So that's my hint to you. So why don't you go and see if you can draw the rest of the slope triangle, and then also write what that slope ratio is, and pause the video, and I'll come back in just a second. Okay, so we've got our first point here. Let's look for another natural crossing point. Well, you might have seen one down here, right at 0, 0, or you might have seen one right up here. Doesn't really matter. I'm just going to go up first for no reason in particular, besides the fact that that's just what I did. So there's my slope triangle that I need to label now. Looks like it's going up 1, 2, 3, 4, 5. So my scale here is 5. Looks like it's going, or is 1, and it looks like my scale is the same on the x-axis. So I should be going up 1, 2, 3 on the y, and I should be going over 2 on the x. So then my slope ratio is going to be that rise over run. So it's going to be 3 over 2, which if I write that as the unit rate from what Ms. Bross was showing us yesterday, we were just saying that we're dividing both of these by 2, because you're dividing by the numerator to get that 1. So this is per 1 year, you're getting 3 halves, or 1.5 meters per year. So my slope ratio here would be 3 halves, or 3 halves meters growing per year. So that's part B. So we've written out the slope ratio. We used our lattice points, and we did the slope of the second graph. Let's take a look at the third part, part C here. Draw the slope triangle for these two graphs here, and then write the slope ratio for each. Definitely convert that down to a unit rate as well. So pause the video here, draw that slope triangle, and write the slope ratio for graphs 3 and 4. Okay, so here's what I came up with for the different sizes here. So let's start with graph 3. So on graph 3, I just always like to go up first, just because it helps me remember that when I write the slope ratio, that my rise comes first. So rise over runs. So I like to go up first if I can. So I chose these 2 points. Doesn't matter what you do, but just choose those lattice points or where the grid marks cross. So 2 over 3, so I've got my slope ratio of 2 divided by 3, which then when I simplified that, and again, we're doing that by just dividing by 3, because we're going to divide by the denominator or the bottom number here to get down to 1 here. So 3 divided by 3 is 1. 2 divided by 3, well, that's just 2 divided by 3. So this tree here is growing by 2/3 meter per 1 year. Now, if we look at number 4, same type of thing here. I'm going to go up first, so I'm going up 2 and over 3. So my slope ratio should be the same thing, 2 divided by 3. And I can do the same approach to get the unit rate, which is divide by 3. So give me 2/3 meters per year. So even though these two graphs look different, they actually are growing at the same rate. Now, some of you might be saying, Mr. Schultz, my triangle looks different than yours. My numbers are different. I might have got something like 4 over 6 or something like that. That's okay. And let's take a look at what that looks like in the next question here. So the next question shows this situation exactly. It says 3 different students looked at the graph at the right and each drew a different slope triangle. Their slope triangles are labeled A, B, C in the graph. Find the length of the horizontal and vertical sides of each slope triangle on the resource page, or we're just going to use the Desmos E-tool. You can click in the lower right to make it full screen. So let's just first find the horizontal and vertical sides of each of the slope triangles. So we're just going to go, and let's start with the triangle C here. It looks like we're just going to count these up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this one here goes up 10, and it goes over 1, 2, 3, 4, 5, 6, 7, 8. So triangle C is 10 by 8. Triangle A, which I'll do in purple here, that's going to be over 1, 2, 3, 4, and up 1, 2, 3, 4, 5. I've got 5 going up and 4 going across. All right, so I think that that you are all capable counters. So when I count out B, it is 12 by 15. So now that we've done this first part of the question, we found the horizontal lengths and we've used our tool and all this stuff. And this part of the question is referring to part of chapter 6 we didn't do. So the last thing is just, what is the relationship between triangles A, B, and C? Explain your answer. So take a second, look at those numbers. Is there a relationship between those 3 sets of numbers? Okay, let's take a look at this. So you might notice that, like, hey, all of the vertical ones, 5, 10, and 15, they're all multiples of 5. And similar idea to the horizontal ones, they're all multiples of 4. So let's see what this looks like in part B. So in part B it says find the slope using the slope triangles. So we've done all that. And now let's just write those slope ratios. So remember, it's rise over run. So for the red one, for triangle C, it'd be 10 over 8. For the purple one, it would be 5 over 4. And for the blue one, I would have 15 over 12. Now, you might be saying, how come all these numbers are different even though it's the same line? I thought that slope was supposed to be the same. Let's see what it says in part C. The number in the slope ratios found by all the students are all different. Does this mean that the slope of the line changes depending on which points you pick? Discuss it with your team. So, does the slope of the line change depending on which points you pick? Think about that for a second. Be a great time to pause the video here. Okay, before we answer that, another student says that her slope triangle goes up 20 units for every 16 units to the right. So now we've got even another ratio here, 20 over 16. Where could her slope triangle be and draw it? Well, I think it could be a bunch of different places. Let's choose this spot here. Okay, so 20 and 16 there. Now, here's our payoff for all this. We've got all these different ratios here. Simplify each of the 4 slope ratios and compare them. What do you find? So let's write all these out and simplify. So here are the 4 slopes. Well, 5/4, that's already simplified. B is 15/12. Well, I see there's a 3 that can go into each of these. So going back to our 7th grade math, I can divide by 3 in both cases. Or, of course, you can just plug this into your calculator. 15 divided by 3 would be 5. 12 divided by 3 would be 4. Hey, that's kind of interesting. Let's see your next one. You can see that a 2 goes into both of these. So again, you can use 7th grade math or use a calculator. And you guessed it, there's a 4 that goes into this. So look at that. All of these here end up being the same thing once you reduce down the fraction. So look at that. Even though there are different slope triangles here, once we reduce it down, they're all the same slope. So this is all the same slope. It's all the same line. So our takeaways here is it doesn't matter where or how you draw it, how big, how small, anything. When you reduce down the fraction, you should all get that same slope if it's the same line. Let's see this one more time in the next problem. So this is problem 745, and it says this: is seeing believing. Did you know that the bank will pay you money called interest when you place your money in a savings account? The amount you receive is a portion of the amount that you deposit. The interest rate often varies with each bank. Thomas and Ryan have invested the same amount of money in different banks that earn simple interest. Simple interest means the same amount of interest is added for each time period. In this case, the interest is added each week. Thomas and Ryan decided to compare their rate of monthly earnings by graphing how much interest each of them has over time. The graphs are shown below. Let's take a look at those graphs. So here are the graphs for problem 7-45. Thomas's is on the left and Ryan's is on the right. A says, when you look at the graphs, which investments seem to be growing fastest? Explain how you decide. Take a second to look at that, pause the video, we'll come back in. Okay, so looking at this, it seems like Ryan's got more steepness, which is what we're finding out in Miss Bross's lesson yesterday. There's more steepness to this line, so we would think that Ryan's is probably your steeper or your faster growing interest. But let's take a look if that's actually true on the next slide. So the tables for Thomas's and Ryan's accounts are shown below. Which table reflects Thomas and which one reflects Ryan? So here we've got this. In 1 week they earned 0.6. In 2 weeks they earned $1. So looking back at that graph, they look something like this. So Thomas in 1 week looks like he's got about that kind of 0.6 mark. And in 2 weeks, well, here's 2 weeks, and you've got about that $1 mark. So probably this is Ryan's. Probably this is Thomas. Let's take a look at part C. So part C says use the tables to find the interest earned in dollars. The interest earned in dollars to time in weeks for each of these. Whose money is growing faster? So we will want to write a unit rate here. So Thomas, you've got 0.6 per week. So he's earning 60 cents per week. Then Ryan is earning $1 every 2 weeks. So get down to that unit rate. We're just going to divide by 2 in both cases. So 1 divided by 2, well, that's just 0.5. So 50 cents per week. So Ryan is equal to 50 cents per week. Okay? Whose money is growing faster? Well, 60 is more. Therefore, Thomas is growing faster. It says, did your answers from part A and C agree? They did not. So the key thing here is just to be intentional about looking at these scales here. Because look, this is only going up to 3 weeks. This is going up to 7 weeks. So, but the y-axis is the same. So depending on how your scales might be doing things, you might be changing as to what things look steeper or less steep. This is super, super common in advertising. It's very common for advertisers to change the scales of graphs or where they start or different things like that to make their product look like it's increasing way faster when it may not even be increasing faster. It may even be less. But so very, very common advertising trick here. So yes, so our last thing here will just be to look at the math note box. So the math note box is just describing association, which remember we're also calling that correlation. You'll see it both ways. I feel like correlation is a little bit more common of a word, but places like Khan Academy use the word association, so it's very common. So positive association or correlation is where it's kind of slanting up here, where as x is increasing, y is also increasing. Negative association is as x is increasing, y is decreasing. And no association is it's random. I can't really see any sort of a trend there. We also talked about this linear versus non-linear form. So you might see associations that have these kind of curves to them where you can say, okay, you can kind of see a little bit of a curve happening here, or maybe this kind of linear curve down here, or just might be just a straight, but also clusters saying, hey, there's a lot of data that happens down here, a lot of data that happens here, but there's not a lot in the middle. All these are just different ways to try to categorize data and move from there. So that's everything that I've got for you today. Have a great rest of your day.